It's too
Okay,
complicated.
so
Okay.
got it.
Got it.
So I get everybody noticed that the thing is being recorded now. That's Walter, not me, but we are recording. So everybody welcome to one but last lecture of this semester. This is by David Kuhl from University of Southern Denmark, Odense. University of Southern Denmark actually covers quite a lot of different institutes. So to be quiet there. And he is going to talk about the metric structure of Podleś spheres. Please,
Exactly.
David.
Thank you. And thank you so much for having me. It's a great pleasure to be able to address a global audience. And before I get started, I should not forget to say that when I get to the research part of the talk, everything I say will be based on various joint works with my former student, Thomas Gottfredsen, my colleague in Odense, Jens Kuhl, and Conrad Aguilar, who is at Pomona College in California right now, but he was with us in Odense for a full year. So all of this grew out of these various collaborations with these people. And I should also come clean right away and say that this is not so much a talk about non-commutative differential topology, differential geometry, as it is a talk about non-commutative metric geometry. So I will consider the theory of compact metric spaces. And for this audience, I guess the guiding principle throughout of your adult life has been this dictionary given by the Gelfand transform. And I've just given you one little page of the dictionary. And what I want to talk about is what fits over here where the two question marks are sitting, namely, what are the non-commutative analogs of compact metric spaces? In other words, if you take a Hausdorff space, assume just a little bit more about it, namely that its topology is given by a metric. How do you model this on the non-commutative side? And this question was dealt with by Riefel back in the late 90s and early 2000s, so it's a fairly new theory. And he arrived based on Kahn's non-commutative geometry.
David, aren't you changing the page? Did you change a page?
I am changing the... Do you see the dictionary?
No, we see just the front page.
Oh, that's terrible.
Only the front page.
I'm already... do you see anything now?
Yeah, now it is there.
Very
yes.
good.
Can you also go to the full screen?
Exactly.
Yeah, I'll just refrain from going full screen. Or maybe I will... how is it? Is it because you share and then go full screen or vice versa? There's some issue.
No,
there.
you can go to full screen.
You can go full screen. It works.
It works. There's no problem.
Let's see. Do you still see the dictionary?
Yes.
Yeah.
Wonderful. All right. So this is the Gelfand dictionary, right? And I've given you some of the more advanced stuff up here, namely the group structure, which corresponds to quantum groups, and the manifold structure, which corresponds to spectral triples. And what I wanted to talk about was just what if you do something less advanced and just demand that there is a metric around, which gives you the topology, how do you model this on the non-commutative side? And this was what Riefel started investigating back in the late 90s, early 2000s. And he arrived at a theory that he dubbed compact quantum metric space. And this is what I want to talk about today. And I guess that there is no need to beat around the bush anymore. I just need to give you a definition of what a compact quantum metric space is. And you, of course, start out with a unital C-star algebra, as you have guessed already. And then the additional data that you need to put on it is that of a semi-norm. So you demand that there is a semi-norm which is allowed to take the value infinity and which is required to respect the star in this way that it is star invariant.
David, again, didn't you change the page?
Yes, I'm changing the page.
But
so apparently, I'll just refrain from the full screen thing. Do you see the text reasonably well now?
Yeah, now we can see it. No, but the questions, if you can just get rid of these borders on your...
The borders.
Yeah, those, so. go to view and something, right?
I think now I stop sharing and I'll start sharing again. I guess people in the chat are complaining about the obvious thing. You don't see the slides. All right, let me try again. I'm now in full screen. Do you see the definition of a compact quantum space?
Yeah,
okay.
We see that. Yeah.
Do you see the first line, the one marked I?
No.
Nope. Okay, no. Never mind. It'll be without the full screen then. This means that I can also better see you guys.
Yeah, that's true. So yes. For
you, I'll leave you guys with
now
the faces out on the right, and then I will continue like that. I hope that you can still read what's written. So okay. Let me start over. So the definition, of course, is that you take units of C-star algebra and you need some additional data. And what you put on it is a semi-norm. And the semi-norm is allowed to take the value infinity, and it's supposed to play well with respect to the star. And then I will require that the kernel of the semi-norm consists exclusively of the scalar multiples of the identity. And I will also require that it's not too infinite in the sense that the domain, the set on which it is actually finite, is a dense subset in the C-star algebra. It need not be an algebra, but it has to be dense. And then the most important requirement, which was Riefel's main insight, is that you want this quantity, this rho L quantity, which as its input takes two states, and as its output gives you the soup over the differences that you get from the two states when you let the input value run not over the norm unit ball, but over the semi-norm unit ball. And this quantity is supposed to be a metric on the state space, and it's supposed to metrize the weak star topology. Okay, so a priori, this quantity rho L could be infinity, but if it is actually finite, it is a genuine metric. And the requirement is that it metrizes the weak star topology. And then this is called a Lip norm, and the whole shebang is called a compact quantometric space. And I, of course, need to tell you where these things come from. And the best thing is, of course, to go to the commutative example. And so if you start with an honest-to-God metric space, X, D, then you can look at the corresponding C-star algebra, C of X, and you can put a semi-norm on it by associating to a function its Lipschitz constant. And this can, of course, be infinite easily, but it is, of course, finite exactly when the function that I'm plugging into it is the Lipschitz continuous function. And these are dense in the C-star algebra, so the two first conditions up here are easy to check. So it's easy to check, the first condition, because the only way you can have Lipschitz constant 0 is if you're a constant function. The third item here is less trivial, and it is a theorem by Rubinstein and Kantorovich that the metric that you get here actually metrizes the weak star topology. And it is a very classical result. This is not how they proved it. They looked instead at probability measures, Rodon probability measures on X, which is, of course, the same thing as the state space. And what they proved was that this quantity basically metrizes the so-called, this is the Monge-Kantorovich or Wasserstein metric on the probability measures. And there's another thing to the theorem, namely that if you view your X as states via point evaluations, you kind restrict the new metric down to X. And when you do it, you get your original metric back so that this Lip norm LD recovers the metric in that way. Anyway, this is, of course, a non-commutative geometry seminar, so I should also connect to something non-commutative right away. And you can easily obtain natural examples from non-commutative geometry. So if you pick up a spectral triple So H is my Hilbert space, A is this star algebra of bounded operators in H, and D is my unbounded Dirac operator. Then it is part of the data that these elements from this algebra A are supposed to preserve the domain of D, and the commutator with D is supposed to extend to a bounded linear operator. So it makes sense to look at the operator norm of the commutator, and doing that, you define a semi-norm, and in many interesting cases, not always, you do get a compact quantum metric structure on the, well, the C star envelope of A in B of H. So, of course, this is the case if you take the classical commutative example. I'm just looking at the unit circle here. With A being the smooth functions and D being the usual self-adjoint version of the differentiation operator. And in this case, the metric that you define on the state space, it'll restrict to the arc length metric down on this one. This is part of a much larger story, namely if you start with the spin manifold and do the same thing with the Dirac operator, you recover the Riemannian metric underneath it. And this goes back to a result by Kohn in the late 80s, I think. But this is still very much commutative, so I should give you some honest non-commutative examples. And here's one, namely the reduced group C-star algebra of a hyperbolic group. So if you start with a hyperbolic group, for instance, a free group, you can look at a finite generating set, and then you can define a length function on the group by simply looking at the smallest length of a word that in the generators that can express a given element. So this is a so-called length function on the group, and you can turn this into an unbounded operator in L2 of gamma by simply taking your standard orthonormal basis and then rescaling the basis vectors with the length of the corresponding group element. And this will give you a spectral triple, and this semi-norm up here will actually turn it into a compact monometric space. This is a result by Takaosawa and Mark Riefel. And you could wonder, maybe there are other good ways of generalizing metric spaces. This was just one way of doing it, but one of the very nice features of this way of doing things is that you can actually generalize the so-called GROMOV.HAUSDORFF distance quite naturally to the non-commutative setting. And this is what I'd like to tell you a little bit about. And this too is actually Riefel's construction. But in order to motivate it properly, I should probably remind you about the classical GROMOV.HAUSDORFF distance first.
Yuri, may I have a question?
Sure, absolutely. So
in this previous example, in order to get a spectral triple, you need to restrict to some dense subalgebra, yes?
Yes, I think I'm just thinking of the group algebra here.
Okay.
Yeah.
Thank you.
Absolutely. Yes, I didn't say that, but please just interrupt me as I go along, right? I think I only have 12 slides that I want to share, so there should be plenty of time for discussion. And I know that quantum metric spaces is potentially not such a sort of a streamlined topic these days. So just ask questions as I go along. Yeah, so I wanted to generalize the GROMOV.HAUSDORFF distance. So I wanted to tell you first about the classical case. So the classical case is really classical. So you take a metric space and then you look at two compact subsets therein, and then you want to define a distance between them. And you do it by means of this formula. So rather than walking you through the formula, I wanted to walk you through a picture of the formula. So I've drawn my set A here and my set B here. And then I have drawn an R neighborhood of B. This is the gray line, which contains A. And what you do is you simply take the smallest R so that A is contained in an R neighborhood of B and vice versa. And by smallest, I of course technically mean an infimum. And this is Hausdorff's distance, and this is really, you can find it in Grundzüge der Mengenlehre from 1914. So this is basically as classical as it gets. And in particular, this is way before Michael GROMOV entered the stage. And his contribution to this part is that he was interested in the situation where you have two compact spaces, but no ambient space within which to compare them. So the more general setting is that if I take two compact metric spaces, I also want to measure a distance between them. And what you do is you look at the disjoint union of the two sets. Then you look at all metrics on the disjoint union, which restrict to the two metrics on the two spaces. And then you look at the Hausdorff distance between the two spaces within the disjoint union. And then you do an infimum over all such distances. And this is the same as looking at all isometric embeddings of the spaces into an ambient metric space and looking at the infimum over the Hausdorff distances in there. So this was actually, so GROMOV got interested in this because he needed a slightly modified version of this in order to prove his famous polynomial growth theorem. And it also turns out to be important in computer science and even in cosmology. But I should also, because to be fair to history, this notion of distance, this GROMOV.HAUSDORFF distance, it was actually discovered by a guy called Edwards a few years before GROMOV got interested in it, but somehow he seems to have been erased from history. So I'm trying to do him justice now. So I think this was what I wanted to say about the classical GROMOV.HAUSDORFF distance. And now I want to tell you how Riefel dualized this to the class of compact quantum metric spaces. So of course, you need to start out with two such quantum metric spaces. And then the natural non-commutative analog of, the dual analog of a disjoint union is a direct sum. And we have already agreed, I hope, that the dual version of a metric is a lib norm. So I want there to be a lib norm on the direct sum. And it's called admissible if the two quotient semi-norms that it induces when you mod out A2 and A1 respectively agree with L1 and L2. And then Riefel noticed that when you look at the two projections there onto the two components, they will of course dualize to injections at the level of state spaces. And if your semi-norm L up here on the direct sum is admissible, this becomes an isometric embedding for the metric on the state space coming from L1 into the metric on the state space and the direct sum coming from this L guy. And then you can therefore compare the two state spaces in this bigger state space. And then Riefel defines the quantum GROMOV.HAUSDORFF distance between the two spaces to be the infimum over all such distances that you can obtain from letting L run over these admissible semi-norms. There is, of course, some things to be checked. For instance, that you can always find such an admissible semi-norm so that the infimum is not infinity, but this is all fine and good. And you can also check, it's not particularly difficult to see that it is symmetric. And with some care, you can also prove, and Riefel did this, that it satisfies the triangle inequality. So we are well on our way to have a reasonable distance function on these quantometric spaces. But there is a little snag, namely that distance zero does not mean what you would potentially like it to mean. Namely, it doesn't mean that you have a star isomorphism between the C-star algebras which preserve the lib norms. It basically amounts to an isomorphism of order unit spaces, or maybe more intuitively, it amounts to an affine isometric isomorphism between the two state spaces with their respective metrics, of course. And I don't want to dwell too much on this, but you can feel right away from the definition that you can never expect there to be a C-star homomorphism coming from distance 0, because the distance function here, the quantum GROMOV.HAUSDORFF distance, it is only modeled using the state spaces. And the state space is completely determined by the self-adjoint elements and the order relation. So somehow you can't expect to be able to recover more than that from distance 0. And this is then, it turns out, exactly what you recover. If you happen to find this defect appalling, I should also say that there are various elegant ways of sorting this out. There is a much more sophisticated version of this quantum GROMOV.HAUSDORFF distance due to Frédéric Lettre-Moulière. It's called the quantum propinquity. And this has the nice quality that distance 0 actually means that you get an honest star homomorphism preserving, intertwining the lib norms. But the upshot, or the price to pay, of course, is that the definition is much more complicated to work with. So I will refrain from doing that and simply stick to Riefel's notion throughout the talk. You might also hope that the assignment that to a compact metric space associates the corresponding quantum metric space is an isometry, but it's not. It is only a contraction, it turns out. So this basically just means that even if you have two classical spaces, you might be able to find a shortcut between them by passing into the quantum world. So it does decrease the distance, but not in a too horrible way, because it is a homeomorphism onto its image. So by that I mean that if you have a sequence of metric spaces, and if you wonder whether the sequence will converge to another metric space, this convergence will happen exactly if the corresponding quantum metric spaces converge to the corresponding quantum metric space. So topologically, it recovers the same information. I would like at this point to also give you a flavor of what can be proven with this quantum GROMOV.HAUSDORFF distance. So one of the early results of the theory is that if you take your favorite example of a non-commutative space, namely the non-commutative torus or the irrational rotation algebra, it does have a natural structure of quantum metric space. And with that structure, if you vary the deformation parameter theta, then the corresponding spaces will vary continuously. Another classical result, which goes back to Riefel as well, and later was refurbished a little bit in a more differential geometric setting by Walter, is that the fuzzy spheres, which are just physics lingo for matrix algebras, they converge to the classical two-sphere as their linear dimension grows to infinity. So physicists, apparently, I'm not one, but they tend to approximate the classical two-sphere with matrix algebras, and Riefel's convergence result here, which is a highly non-trivial result, shows that this sort of intuitive approximation can be made rigid in the sense of convergence in the quantum GROMOV.HAUSDORFF distance. You can also deal with certain cross products. So if you have a quantometric space and a suitable automorphism of it, you can ask whether you can induce on the cross product a quantometric space structure, and you can. And under reasonable assumptions, if you start varying the automorphism along a continuous path of automorphisms, the corresponding family of cross products will vary continuously. You can also prove that AF algebras are approximated by matrix algebras. This sounds maybe like a tautology, but because this is how matrix AF algebras are built. But I of course mean that if you have an inductive limit, say of matrix algebras with each their quantum metric structure, under reasonable assumption, you can build a quantum metric structure on the inductive limit, the AF algebra, and then the convergence will actually take place in quantum GROMOV.HAUSDORFF distance. However, there are in non-commutative geometries, some of the most basic objects are these Q-deformed spaces, and they seem to be less well understood from the quantum metric point of view. At least in a way that reflects the non-commutative geometry. And maybe I should pause for a second and try to explain what I mean by this afterthought here, because this is a question that arises quite often in this topic, namely, what is a good quantum metric structure? Because there are these metrization theorems saying that if you take a second countable compact topological space, you can always find a metric on it that gives you back the topology. And you can do something similar in the non-commutative world. You can prove that if you take a separable C-star algebra, you can always construct a semi-norm on it, which turns it into a compact quantum metric space. However, you might not be much wiser after having done so. You often want a metric which somehow encodes some sort of underlying geometry. Imagine that you had taken the unit circle. The natural thing to measure distance there, I guess, is the arc length. And if you just forget all of the structure, except for the fact that it is a second countable topological compact space, you would get another metric which gives you very little information about the geometric structure. And what I want here is, I really want somehow a quantum metric structure which is built out of a certain non-commutative geometry. So I want, in essence, a non-commutative version of a Riemannian metric. And I don't know how to quantify this properly, but I want to somehow convey the underlying idea to you anyway. So just to stress how little we understand at this point, it was actually only a few years ago that Konrad and Jens showed that the Dirac operator, the Dabrowski-Sitas Dirac operator, which gives you a spectral triple on the Podleś sphere, will indeed turn it into a compact quantum metric space. And this means somehow that the non-commutative geometry here fits well with the metric aspects of things. And I would like to talk much more about the Podleś sphere. So maybe I should set the stage a little bit for Q deformations. And I will be brief because most of you have met these things already. But I wanted to quickly recap some of the definitions, because at some point I really need to get underneath the surface just a little bit. So so you probably all know from a topology class at some point that you can view the two sphere as a quotient of the free sphere, or the quotient of SU2 under a circle action. This is the Hopf vibration. And if you're a non-commutative person, you will right away see that this dually should be thought of as the continuous functions on the two sphere being a fixed point algebra of the continuous functions on the SU2 group under the corresponding circle action. And there is this famous quantum group, SUQ2, due to Vodonovich, which gives you for each Q between 0 and 1, generally non-commutative C-star algebra. And this is true, the non-commutativity is true as long as you stay away from 1. But exactly when you get to Q equal 1, you recover the continuous functions on the classical SU2 group. And the good thing, or one of many good things about this C-star algebra SUQ2 is that it also has a natural circle action. And this means that you can mimic the definition up here and define a Q-deformed two-sphere by simply looking at the fixed point algebra of SUQ2 under this circle action. And this is what Podleś did many years ago. And therefore, these Q-deformed two-spheres are called the standard Podleś spheres. There are non-standard things as well, but I'll not get into that. So I'll just erase the adjective standard and just say Podleś sphere. Now, if you want to be a little bit more concrete about it, this C-star algebra, the C-star algebra, which is the non-commutative analog of the two-sphere, is generated by two operators, one called A, which is a self-adjoint element, and then a non-normal B. And if you then take the C-star algebra generated by those two guys inside this bigger C-star algebra, you exactly get the C-star algebra, which is the Podleś sphere. And as I already told you, it is so that this C-star algebra, it has a natural Dirac operator associated to it, the one that was investigated by Dabrowski and Sitash back in 2003, I think. And as I already also mentioned, this construction of taking the norm commutator semi-norm turns it into a compact monometric space. And the way that I have sort of set the stage right now, there is one question that is staring at you, namely, will these Q-deformed spheres with their quantum metric structure actually vary continuously as Q varies, so that we can say that the Podleś spheres do converge to the classical two-sphere with its round metric when the deformation parameter Q tends to 1. And this is what we set out to investigate, and it turned out to be difficult. So when things are difficult, you need to make them more difficult or less difficult. And we decided to make them less difficult. So we decided to sort of decrease the problem a little bit and just zoom in on this self-adjoint element A. So remember this guy C of SQ2, the C-star algebra, was generated by a normal, a self-adjoint A and a non-normal B. So we only look at the C-star algebra generated by the self-adjoint element, and this is of course a commutative C-star subalgebra. And it's quite easy to compute the spectrum of this AQ. It is namely a sequence of Q powers which is converging to 0. So the spectrum consists of this sequence Q to the power 2k and its limit 0.0 when Q is away from 1. And when Q is equal to 1, you get a genuine unit interval as the spectrum. So I guess it makes sense to think of these spectra of AQ as sort of quantized analogs of classical intervals. Now, being a sub-C-star algebra of a compact quantum metric space, the Lipschitz semi-norm up here will restrict, and it turns out that the restriction here is again a Lipschitz semi-norm. So this C-star algebra, this commutative C-star algebra, it automatically gets a compact quantum metric space structure on it. And because it is, of course, the continuous functions on the spectrum, this quantum metric structure will induce an honest-to-God metric down on the spectrum that we call DQ. And similarly, at the fiber 1, you can repeat the whole story. So this C of 0, 1, which is just the C-star algebra generated by the self-adjoint operator at Q equal 1, will get a quantum metric space structure from the quantum metric space structure coming from the round metric on the 2-sphere, and hence it'll define a metric on the spectrum 0, 1. All right. But this metric D1 will not be the ordinary Euclidean metric because it, of course, comes from the round metric up on the 2-sphere, and therefore it turns out, and it's not too difficult to show, that the metric that you get here, or the metric space that you get here, is isomorphic to the interval from 0 to pi with the standard Euclidean metric. I think one should really think of it as you have a round 2-sphere, and then this spectrum here is stretched out half north-south pole circle. So this is why the metric becomes what it is. And what is more complicated is to understand what this DQ metric is on the quantized intervals. And this is what we did together with Thomas Gottfredsen, Jens and I last year. So it turns out that you can actually write down a concrete formula for DQ. So given such two Q powers, you get a certain sum of positive numbers, which is the metric. So you can write it down fairly explicitly in terms of Q. And once you've done that, once you understand the metric well enough, you can prove that these quantized intervals, they do indeed converge to the sort of the expected limit point, namely the 0 pi interval with the standard metric in the GROMOV.HAUSDORFF distance. So note, this is all completely classical. These are classical spaces. This is a classical space, and the convergence is with respect to the classical GROMOV.HAUSDORFF distance. But as I already told you, it of course also holds true if you consider them as quantum metric spaces, because this assignment, which passes from a space to its continuous functions, is a contraction. So if they converge classically, they converge even more so quantum. So we decided to take this as a sign that potentially one could actually hope for more sophisticated non-commutative convergence results. And this was the point when Conrad arrived in Odense. So we had additional manpower for a full year. So Jens and I and Conrad, we set out to prove this. And it turned out to be a little bit tricky. So after, the usual 15 to 20 failed attempts, we finally figured out how to properly attack this question. And then we proved that the standard Podleś spheres, SQ2, they do vary continuously in the deformation parameter. And this also holds at 501, so that the quantized 2 spheres really do converge towards the classical 2 sphere with its round metric as Q tends to 1. Now, at this point, you might start to get upset with me, and rightfully so, because I have been deliberately sloppy in my way of formulating the theorem, because I've written it in such a way as if these quantized spaces actually do exist, and they don't. We all know that. They only exist by means of certain algebras, and I should specify what is the domain of the Lip norm for this convergence result. And let me tell you that, so that you can hopefully stop being upset with me. This is really an algebraic theorem, the way we proved it at least. So there's a theorem about the coordinate algebras. So remember, the Podleś sphere was generated by A and B. So I can look at the algebra that these operators generate together with the unit, and this will give me a nice, dense subalgebra inside the C-star algebra. And by definition, these will be the domains of the lib norm. So I only choose this formula, the norm of the commutator, as long as x is in this coordinate algebra. And by definition, the lib norm is set to be infinity outside of the coordinate algebra. So this is really like when you look at the paper, you will see that this is really a Hopf algebraic theorem. And you might object to this because you might be an analysis person or a geometry person and not an algebra person, and say, but David, the right domain of the lib norm is of course the maximal domain, right? You can look at all possible elements in the C-star algebra for which this formula makes sense. So you can look at all possible elements which preserve the domain of the Dirac operator and for which the commutator extends boundedly so that this is a finite number. And this is a reasonable objection. So this corresponds to looking at the Lipschitz functions on a classical manifold. And in order to sort of deal with this difference, we wrote a follow-up paper in which we prove that it doesn't actually matter. So what we prove is that the distance, the quantum GROMOV.HAUSDORFF distance between the Podleś sphere with its minimal Lipschitz semi-norm and the Podleś sphere with its maximal Lipschitz norm is actually 0. So whatever convergent result holds for the minimal also holds for the maximal, or anything in between, of course. And now you might start feeling upset again with me, because does this really justify being called a theorem? Because you might think at this point that this is just a matter of, you know, looking at the derivation that comes from taking the commutator and then passing to the closure and making sure that everything matches up. But it's actually slightly more subtle than that, because if you close up the derivation that comes from taking the commutator with the Dirac, then you get a smaller algebra than this guy. You get, in the commutative case, what you get is the C1 functions. And there's a gap between C1 and Lipschitz, and this is the gap that requires a bit of work to fill. And actually the work that has to be done is somewhat more for Neumann algebraic than C-star algebraic. So this requires some von Neumann algebraic work, and you might be surprised to hear that at first, but you shouldn't be, because if you start differentiating a Lipschitz function, you can actually do that, but you can only do it on a set of meshes, on a set of full measure. So what you get is not a continuous function, you get a measurable bounded function, which means that you're in an L-infinity algebra, and therefore in a von Neumann algebraic realm already. So this is why this argument requires a little bit of extra care. But I don't think that I would like to dwell more on this last theorem, but I would like to talk briefly about the main ingredients in the proof of the main theorem, because there are some interesting things going on in the proof that I think deserve to be brought out into the light a little bit. So if you can indulge me for a slide of slightly more technical things, I would like to walk you through the main argument, because
just one question.
Yeah, absolutely.
So this last theorem also holds for Q equal to 1?
It does. It does.
Okay.
And maybe,
surprising.
Yes, we tried to find. So we tried to find the corresponding result in the literature, and we didn't succeed. So we made a little note in the paper that this is probably well known in the commutative case, but we couldn't really find it. So if anyone happens to know So yeah, I should maybe backtrack a little bit. So basically what you need to find here, if you are given a Lipschitz function, you need to find a polynomial which approximates the Lipschitz function well in norm and does not have a larger Lipschitz constant than the function that you started with. And I'm guessing that this should be somewhere in the literature in one way or another, but we didn't really find it. So yeah, we came at it from a completely different angle, of course. So yeah. Any other questions before I continue? So what I wanted to show you was the sort of main strategy, because the main strategy actually sort of contains an interesting result in its own right, I think, because the key to the proof is to construct quantized analogs of fuzzy spheres. So remember, I talked about this fuzzy sphere result of Riefel, that the matrix algebras converge to the two-sphere. And what we find is for each Q, we find a finite dimensional subspace for each natural number n, such that when this natural number n grows, the finite dimensional subspaces will grow up to the Podleś sphere in quantum GROMOV.HAUSDORFF distance. And this Fnq here is actually n plus 1 square dimensional. So from a linear point of view, I guess it deserves to be called a matrix algebra. So we think of these as Q-deformed analogs of fuzzy spheres. And if so for each Q, we now have Riefel's convergence result upwards in the linear dimension. And you can actually, if you look at this proof of our little test result, namely that these quantized intervals approach the classical interval, you can actually use this extremely concrete formula for the metric on the spectrum of A to show that this convergence is suitably uniform in Q, meaning that if you're given a certain tolerance and you move your parameter Q close enough to 1, you can actually make sure that from a certain n onwards, all these fuzzy spheres are close to the corresponding Podleś sphere. And then the last ingredient in the proof is to do the things the other way around, and that you now fix the linear dimension of your quantized fuzzy sphere, and then you let the deformation parameter Q vary instead. And it's not too difficult to see that these fuzzy spheres, these Q-deformed fuzzy spheres, they will converge as Q tends to 1 to the corresponding fuzzy sphere at 501. And now the game is over due to the triangle inequality. So rather than walking you through more computations, I wanted to just sort of illustrate what is going on. So here, down here, I have my deformation parameter Q, and over the number 1, I of course have my classical two-sphere, and then for each Q, I have a Podleś sphere sitting there. So if you now imagine that someone gives me an epsilon, I can find a suitably big fuzzy quantum sphere, sphere in here that approximates really well the Podleś sphere. And now I can start floating in the deformation parameter all the way up to the 501. And because of this uniformity business up here, if I don't float too far away from 1, I can control the error that I make compared to the epsilon that I was given. And then, because these finite dimensional spaces converge, again, if I go close enough to 1, this FNQ guy will be as close as I want to the corresponding FN1 guy. And now the game is, of course, completely over. This means that the Podleś sphere, which was close to the FNQ guy, which was close to the FN1 guy, which was close to the classical sphere, is close to the classical sphere. So I guess this is a good place to stop. So thank you so much for your attention and for joining in to this virtual seminar.
Thank you very much for a nice lecture. Questions, comments?
Yeah, I have actually 3 questions, if I may.
Okay, go ahead.
So first question is the following, and let me write on your screen, David, if you don't mind, it will be more clear. So you know that if you have a C-star algebra of a Podleś sphere, and you take a different Q, sorry, that's to Q prime, that they're actually isomorphic. This is not true, however, for polynomial algebras. If you do it like this, then actually they are pairwise non-isomorphic. So you can write that O of S2Q is equal to O S2Q prime. This implies that Q is equal to Q prime. And in the C-star algebraic result, I mean, it's simply, you can take Q equal to 0. You exclude the case Q equal to 0 in consideration because then SQ2 ceases to be a quantum group, but it's still a graph C-star algebra, and that's how you look at it. So am I right in thinking that in fact when you do this convergence business, at least for C-star algebras, what you are simply talking is about the convergence of one metric to another, because that's the same quantum space all the time?
I guess, I mean, you're absolutely right. You can look at the Podleś sphere C-star algebra as just a unitized version of the compact operators.
Yeah, exactly.
So you can, of course, if you take this point of view, you can look at it as different quantum metrics on this fixed C-star algebra, which then converge to a classical space. But yeah, well, I don't know. This was one of our 25 failed attempts. It didn't work well to think of it like that, so we went back to thinking about it as different algebras instead. But of course, like, I mean, from a sort of legal point of view, you are completely free to do the latter, or think of it as compact operators plus the unit. Did that answer the question?
Yeah. And in this algebraic case, where these algebras are actually pairwise non-isomorphic, which is not such an easy result, but it's true, these algebras are all different. But this didn't somehow matter to you in your reasoning, because you treated in both cases, C-star and algebraic, you treated them as simply different algebras. You were not taking any advantage of the isomorphism, right?
Maybe yes and no. I mean, so I guess, well, maybe not. So the computing the spectrum, I guess, of this A, what you do is you represent it as compact operators, right? So this is the first place where we certainly do take advantage of it. Secondly, the result prior to these papers is that the Dabrowski-Sitas spectral triple does actually give you a compact monometric space structure, and there it is used heavily. This is really the pivotal idea, is to use this isomorphism with the compact operators. So somehow it's happening one level under our results, but certainly used.
Yeah. And you use these compact operators also in this algebraic case.
Sorry, one more time?
And you use this compact operators representation also in this purely algebraic case.
Yeah, but yes, but it's sort of a little bit hidden.
Yeah, okay, good.
Yeah.
Good, thank you so much. Now, my second question is, how about other Podleś quantum spheres? So if I have this S Q infinity, the equatorial Podleś sphere, do you also have a similar result of convergence?
It's on the to-do list. It's on the very long to-do list, because there are a lot of really natural open questions here. But yes, it's on the to-do list, but I haven't really haven't really touched it at all yet. Maybe I should also, there's another question that could be raised at this point, namely, what about the quantum SU2?
Yeah, exactly. Yes.
Yeah. This is also, yes. We are hard at work, Jens and I, dealing with quantum SU2, but I'm being recorded, so I will. My statement will forever survive online. So rather than making any bombastic statement that turns out to be blatantly wrong in a few weeks, I'll just stick to saying that we are hard at work, and I think it's gonna crack.
Okay, thanks. And my final question is both to you and Makoto, actually. So some time ago, Makoto proved a Q-deformed version of the famous Borsuk-Ulam theorem, which, as you know, involves spheres. And he used KK equivalence, used the continuity of the field of sister algebras, of spheres, and so on and so forth. And he reduced the quantum version of a Borsuk-Ulam theorem to the classical one by a very tricky KK argument. But he used this continuous field of sister algebras. Now, I'm wondering, could this convergence technique, imagine that you can prove such a convergence for all, say, quantum spheres, would it be helpful to know such a convergence result in reducing some Q-deformed version of the Borsuk-Ulam theorem to the classical one? Because it's somehow an alternative to having a continuous field of sister algebras.
David, after you, maybe.
I was going to pass it on to you. The short answer is I have no clue, but it would be lovely if it were the case.
Well, right out of my head, so I don't really have intelligent thing to say, because this one doesn't really look like very compatible to that kind of sort of argument with really something like Lefschetz number. But still, I mean, so there was newer proof by I have to be more his, but so there was a newer proof that was more that had more clever reduction to classic Borsuk-Ulam theorem, and so I guess I have to. Yeah, so that line of reasoning could be a good work, and maybe you can adapt this.
Okay, thank you so much. This was a lovely talk, by the way.
Hey, Thomas.
Yes.
So you raised the hand, right?
Yeah, me too. I enjoyed your talk. You mentioned that the GROMOV.HAUSDORFF distance has an application in cosmology. Could you give us a taste of this application?
Oh, I wish I could, but I'm not a physicist myself. I just read up on it a little bit, so I really can't. I really shouldn't. Certainly not while being recorded. It's just I wanted to sort of advertise that it had applications outside of pure math.
Okay, thank you again.
You're welcome.
Can I have a question? Yes, can I have a question?
Yeah, sure. Go.
Hi, David. Good to see you. By the way, this is my only opportunity to see you during the seminar, so very nice.
If you guys don't know, they are from the same institute.
Yeah. Well, we haven't met in half a year.
Yeah, well, a year and a half, yeah. Okay, but my question is, so first, maybe somewhat related to what Piotr said. So you excluded actually the case Q equal to 0, which for some people is actually the most interesting case. And so my question is, do you know what the limit of these metric spaces is when Q approaches 0?
Well, the metric spaces, yes. So they do actually converge to a 2-point space. So at the fiber 0, this operator.
The 2-point space, you mean the Podleś spheres S to Q converges?
No. I meant the intervals.
Yeah, the interval. I sort of can see that.
Yeah.
But I was asking actually the Podleś sphere.
I don't know. I haven't figured it out. And I don't even know whether it is particularly difficult.
Okay.
Actually, I'm not 100% sure if the Dabrowski-Sitash Dirac operator at Q equals 0 works well.
So that was my related question. I mean, because one thing would somehow correspond to the other, but of course the algebras are perfectly defined both on the sister algebraic and pure algebraic level. Here there is no problem, so it would be very surprising if this metric somehow behaved strangely at this Q equals 0 limit, but I would like to be sure. I thought maybe you guys knew the answer.
We haven't really thought about it, to be honest. We focused on the other end of the interval, but it's a completely valid question that also should be investigated, together with the more generalized Podleś spheres. There are many, yeah.
Mm-hmm. Yeah, because the question is simply whether this Dirac operator of Dabrowski-Sitash is more banking on the Hopf vibration structure, which is perfectly well preserved in terms of graph sister algebras at Q equals 0, or whether it uses a coproduct, whether it uses quantum group structure of SUQ2. And this I just don't remember.
Well, I mean,
that would be fine.
That's not the case, actually. So, and I don't think it's compatible with the Hopf vibration, right? So,
Dabrowski-Sitash?
Yeah, it's a completely different. I mean, in fact, the one on quantum SU2 is typically the isospectral one, and it's not at all the one that you get on the Podleś if you take like the U1 invariant part. So that's actually a very difficult. I mean, maybe Jens, he focused a lot more on that aspect, I think, but I'm not sure if he's around. So I would say that's not so clear, because indeed for the quantum SU2 case, this is what you do. You kind of take Q equals to 0. And try to work with that, because that works rather easily. But on the Podleś, I don't think the Dirac, I mean, it doesn't make sense for Q equals to 0.
Okay, this I didn't remember. And don't they use these quantum Hopf line bundle sections as the Hilbert space for the Dirac operator?
The Dirac operators, it is defined via the pairing with the deformed Lie algebra. So you get an action of the deformed Lie algebra on the coordinate ring, and this action is used to define the Dirac operator, because you can imagine somehow that the deformed Lie algebra will give you certain derivations or twisted derivations, and this is how you define it. So unless you have, well, I should refrain from making bombastic statements, but it seems to me that unless you have the full Hopf algebra duality working out, it's difficult to define a good Dirac.
No, so this would be compatible with what Walter just said, because this requires Q to be away from 0.
Yeah.
Exactly, and to confirm, I mean, on quantum SU2, it's not, the construction is not like that. I mean, not using these Lie algebra of quantum SU2 to define the Dirac operator. So it's different. So no, it's an interesting question. So Jenny?
Can I comment on that? There is, on quantum SU2, there is a spectral triple by Chakrapot and Pal, which is singular and is compatible with Q goes to 0 limit. And Alan did some work on the index theorem over there. So that one could be more suitable to analyze in your context.
Yep.
It's one of the first examples of actually spectral triple on quantum groups, but it's a singular one. So that one is really.
By whom did you say? Chakrapot?
Chakrapot and Pal. It should not be difficult to find. And there is a related paper by Alan. It's a very long one where he just considered the index theorem and he shows that it fits perfectly. And it does all the computation Q is equal to 0. So just because it's so much easier.
Makoto wrote the names. Thank you. I'll just copy paste them shamelessly. There we go.
Can I ask one more quick question? Since Piotr asked 6 questions, I can ask.
Well, excuse me.
Go ahead. Come on, Wojtek.
Okay, so I would like to ask about these finite dimensional subspaces FQN. that you used in your under the hood. So these were subspaces actually chosen from the polynomial algebra, right?
Yes.
So do I understand correctly that they were actually not subalgebras?
They're not.
But is it the intuition that somehow from metric point of view, they should be close to metric spaces built on matrices, on matricial approximation to sphere? Is that the intuition?
Well, I mean, so in the classical case, the fuzzy spheres aren't subalgebras either, because well, of course they're non-commutative, so they can't be subalgebras of a commutative.
No, but they are themselves algebras.
Exactly. But what you have is
with matrix algebra.
Yeah, you have this Beretson, it's called the Beretson symbol, and it's adjoint, so that you can somehow map them. That you can map your honest-to-God matrix algebra into the continuous functions. Yeah, and this is it's basically the image which approximates, and we only have the image, so to say. We don't have the Beretson symbol. We go straight to the image, which is then just a square dimensional subspace.
Okay, so maybe something related here. So it seems to me that you somehow never, in your argument, you never viewed the algebra of Podleś sphere as AF algebra. You never took like kind of advantage of the AF structure. This seems a bit surprising to me, because a lot of body of work has been done, right, on this aspect of AF algebras, and I would be surprised if there is some kind of relation between what you are doing and the previously done work, a lot of which was in Copenhagen, right, on these kind of things for AF algebras, but you somehow never look at that.
So my problem there is that I need somehow a way of passing down to my approximating finite dimensional structure in a way that does not increase the lip norm. So I want somehow a lip contraction down to this this finite dimensional approximation, whatever the finite dimensional approximation should be. And then you need somehow the AF structure to be compatible with the Dirac structure. And I don't think this is that obvious.
No, I mean, it is only compatible in the case Q equal to 0. Okay. But my point is that there must be some metricial maps on, that are close in the metric aspects between them. I mean, it is at the end of the day, it is an AF algebra, and this kind of, so it just, you haven't looked at it from that point of view. That's what it seems to me.
There are, so if you turn things around and look at, really take it seriously as a limit, as an AF algebra, you can use the quantum metric structure on the matrices to build a compact quantum metric structure on the limit, on the AF algebra, so that you do get the convergence. But then there is no way of ensuring that this quantum metric structure is in any way geometric. So this is our sort of the recurring sort of mantra in the work is that we don't want any old quantum metric on the Podleś sphere. We want something which is geometric. We want it to come really from taking the commutator with the Dabrowski-Sitas Dirac. But I'm not saying that it's impossible, what you're suggesting. I'm just saying that we couldn't make it work like that. Yeah.
Thanks a lot.
So apropos questions, did you guys try to compare the distance, right? So you have two different metric space structures on compacts interlaced. One is the one you're working with, and the other one is because it's AF. I saw the one by Eric and Christina, right? They had this compact matrix structure on that. Did you try to compute distance?
We didn't.
No.
This could be another way to go around it.
Checking what's happening.
Yeah.
But it could be as difficult as this distance zero theorem that you presented, right?
It could easily be.
It could be easily difficult. Yeah, of course.
I think I'm not in any way trying to suggest that this is the only way to go about the proof, but I really like this the structure of being able to sort of mimic Riefel's proof in each fiber, and then use this fuzzy sphere approximation to pass down to something finite dimensional, and then float along the fiber continuously, and then control the mistake that you made. But you're right. It could be that they have distance zero, and then they're equally good.
Yeah, but so proper approximation. This is just truncation of a spectrum of AQ, or what?
What is the finite dimensional one?
Yeah, this approximation.
Nope. It's actually it's generated by certain polynomials in A and B. So, or in other words, you take out. So, I don't know. It's getting it's getting a little bit technical, but you know the Podleś sphere well, I suppose. So you have all these unitary co-representations of SUQ2, and the Podleś sphere comes from taking all of the middle columns.
Yep.
You take all the middle columns up to degree n, up to the nth co-rep. Does that make sense? So you fill it up like that.
Okay.
By the way, please remind me, there's Dombrowski-Sita's Dirac operator. How does it behave at q equal 1? Is it the standard one? What is it?
Yes, it is the standard one. Yeah.
Okay, we are getting somewhere. So more questions?
May I have a question?
Go ahead, Adam.
So this Podleś sphere, the metric dimension of the Podleś sphere are 0, yes? Am I correct?
So in what sense of metric? What do you mean metric dimension?
Like the summability of the Dirac operator.
Read from the growth of eigenvalues of the Dirac operator. So suddenly in the limit, you get something which is two-dimensional. Yes.
Yeah.
So, do you know some natural class of examples where the opposite phenomenon happens? Then the family has strictly bigger dimension, and then if you go to the limit, then suddenly the dimension drops.
Not on the top of my head, right? Because what usually happens is this phenomenon, right, where you have a dimension drop when you pass from the commutative to the non-commutative world. You see, at least cohomologically, that the dimension will drop by 2, which I guess is the same 2 that drops here, right? So no is the short answer.
Okay, and maybe just one more question, if I can. Also a general question. So is it known how big is the set of all classical compact metric spaces within the set of all quantum metric spaces in the sense of quantum GROMOV-Hausdorff distance?
I don't think. Do you mean if there is like a density argument or something like that? That every
something like this, nowhere dense. I would expect that this set would be nowhere dense, but I'm not sure.
Yeah. I don't know of any such statements, but it's a curious thing to investigate.
Okay.
I will stick to my strategy of not making bombastic statements about things that I haven't thought about in advance.
Okay, thank you.
You're welcome.
Okay, shall we? Any more questions? So, shall we say thank you again for a very nice lecture? Thank you, David.
Thank you for having me. It was a pleasure.
Thank you. And see you guys in a week's time.
Absolutely.
Till then. Bye. Hi.